With where we paused on Monday, we went over the mistake that's here. Notice that it is trying to do a linear search in a list of numbers called scores, checking if it has 37. And this misplaced else, notice it's inside the for loop, would cause this code not to work. It returns false, only checking the first number, but this array has 37 inside. So the correct way was to go something like here, like this. Return false happens outside the loop. Very easy mistake to make. With our next example, it's a classic searching kind of problem. You're looking for adjacent elements, so kind of like what we did for your game of life with the neighbors. Here, we want to use a linear search, so you should be thinking of linear search for loop. We're going to see if there is a 3 next to a 7 in the array. So you can imagine the first part is writing a for loop. The next part, since it is a linear search, you write some kind of if statement. In this case, we're looking for 3 being at position I, and that 7 being at position I plus 1. That's what it means to be next to. If we see that kind of situation, then we return true. Otherwise, when we're done stepping through our for loop, we return false. Again, here, notice the code does not have the squiggly braces. You have to get used to reading this. If your for loop or if statements contain just one line of code, then on the AP test they omit the squiggly braces. So you may have to pencil those in or just get used to reading stuff like this. Notice here in this example there's no indentation to show you that the if statement's inside the for loop. This is something you gotta know. But when we look one forward, a very easy mistake to make is to go out of bounds. So could you type in chat, if we're preventing ourselves from going out of bounds, what should we put in these orange or brown question marks? What should our stopping point be? Very good. You guys see it? If we're looking one ahead, then we have to stop one early. We have to balance whether we added or subtracted from there. So scores.length minus 1. Stop 1 before the edge because you're going to look forward. Yes? Let's look before you jump. So we can extend this one more. If we modify this function a little bit, if we look over 2 elements to see that is 3 in position I and is 7 in now I plus 2, how do you think this stopping point changes? What number should now go into the orange or brown question marks? We're looking 2 ahead. Yeah, you see the pattern? If we're looking 2 ahead, then we stop 2 before. This idea comes in useful for one of the coding back problems. Scores clump. This one involves like looking at 3 numbers at a time. Often you will get an array out of bounds error depending on how you code up the 3 numbers. Is it I plus 1, I plus 2, position wise, or is it at I minus 1, I, and I plus 1? So depending on your implementation, you will likely have that error present in scores clump. I hope this adjacency problem using linear search helps you with that. Sticking with the linear search idea, we'll now jump to finMin. We'll go over the recursive way of implementing finMin. The slides go over the loop way. And then, if there's time, we'll go over an example with binary search with the goal of trying to review binary search list. But if you want a hint for binary search list, you can jump straight to a particular slide, this one here. Yeah, jump to slide 58 if you want immediate help on binary search list or binary search. And you can just use this slide and fill in the question marks to get it. Okay, so in the spirit of still working with linear search algorithms, find minimum, classic computer science problem. Given in a list of numbers, you are to find the smallest value in that array. So here we have these numbers, the minimum value is 2. Here we have these numbers, it's located at the very first position, but we still got to check everything. Minimum number is 6. Find minimum in this list of 1s and 0s, it's a 0, and that minimum was repeated a bunch of times. So, as you think about this problem, for sure, you got to think, okay, if I'm looking for a minimum, I gotta have a for loop, I gotta have an if statement, and because my minimum can change, right? If I'm looking through my for loop, there could be a temporary minimum. I can assume that I start at the first number and then see that, guess that is my minimum. And then as I walk through my list of numbers with my for loop, my minimum may be updated. So to start us off, we're creating this local variable, int min, and we're going to start it off at a certain number. Just like I said, we're going to assume the 0, or the first number, is going to be my minimum. We haven't yet written the code that compares it with all the rest. That will be coming up. Next, as we do with most coding back problems, we take a look at the return type. We see that it is of type integer, so we should be returning an integer. This point is emphasized in this slide because on the FRQ grading rubrics for the AP test, that's one of the easy points to get, that you returned you return a variable on something that matches what it wants. So in this case, it's an integer. Click. Yep, so this slide mentions just that. Next up, in our question marks, we gotta start writing our for loop. So where do you think we should start if we're looking for the minimum? I've stored the very first thing into min. Now my for loop has to start these comparisons. Yeah, so that could work. You could still start at position 0. If you want to be a tiny bit more efficient, since we already are assuming that minimum is that first number, you could write code that starts at 1. But your code would still work if you started at 0. I don't think it does any harm. And the other parts are pretty standard. You have to check your entire array. So you go through till the length, I plus 1. You can imagine now, next step, once we have our for loop, we have to utilize and write some kind of if statement, right? We have to do some kind of checking. So if something is less than my minimum, this would be the if statement. What goes into the yellow question marks? It's more than just I. Remember, I is the index, and we're working with an array, so you must use that index with the array. There we go. A list square bracket I. Very good. It's very easy to get the indices and the element at that position, at that index mixed up, especially with searching and sorting. Very good. So a list square bracket I, if that thing is less than my minimum, you're translating the English sentence like, update your minimum to be this new number. You found something smaller. So we got to store it. Min equals, you guessed it, a list of I. And this is the answer for the first finMin problem. Next up, we will review the recursive finMin function. And maybe I'll just step through a couple of examples. Last class, it took me a while. I had to take a little break. I couldn't come up with an explanation during class. So then I'll do it for you all. Doing okay on time? Yeah, we're doing plenty great on time. So find minimum, but this is not the one I want. This one you could use a loop for. We want the second one, find minimum with an H next to it. This one wants you to do so recursively. Oops. There's your answer. So here, notice that we're writing a recursive method. The input is an array, and then there's a size that returns the minimum element. This method gets the array and its size as parameters. The array will have at least one element. Let's see. So we'll peek at the test cases. Notice that you have an array of 1. It's kind of easy. You see that this number that's returned, it has to be that single element that's in your array. When we have 2 elements, this thing has to do one comparison. You have to compare these 2 positions and find the smaller of the 2 and return 0. Then for the rest of these, the arrays gets much longer because this is the part where it becomes recursive. If you're thinking about the base case, you actually have 2 base cases here, and that wasn't obvious to me at first. I had to walk through some examples, namely these 2 test cases, right? This part, you can't really recurse on this. You haven't done any comparisons just yet. You have to compare, like, the simplest version of this problem is an array with 2 numbers. You either return 0 or you return 1, and you have to do an if statement to check whether or not you, which of these 2 are smaller. I think it's worthwhile to step through how this recursive algorithm would work for like 0, 1, and 3, for example. Okay, so if this is my input, the recursive bit could do something like, okay, I have to process 0 and 1 as an array of length 2. I'm going to use this AND symbol, and you have to check it compared to this number, right? The one at the very end. This part here, you have to recurse, like you have to call your like find min of your array of size length 2. This is one of your base cases. If there's 2 numbers, you're going to write the code to do the comparison. So this is the recursive call, and then you compare. Okay, whatever find min returned for 2 numbers, you're going to compare it against your third element. In this case, it was a 3, which is the smaller of these 2, and then return that number. Right? Find minimum returns a number. If you do it with like 4 numbers, let's mix it up. 1, 5, say zeros here, and 4, okay, your code should be addressing, okay, find the minimum amongst 3 numbers in your array, and then address that and compare it to your last number. I'll give you some code now. I kind of worked through some examples. Clear. So here's your first base case. If your size equals 1, right, return that number. Let me zoom in a bit. Not too much. Yeah, maybe one more, that's okay. Then, if your size is 2, you gotta still do some number comparisons, right? You have 2 options. Either array at position 1 is bigger than array 1, in which case you return AR, or actually I'll leave that blank, up to you. Return like something. Or you have the other case, right, where you return something else. There's only 2 options. Should this be an else if? I think we're fine. Double check my parentheses. This is the one where it's end size equals 2. So then my else statement could go here. Or we can write it like this. Size is bigger than or equal to 3. This is the part where we have to recurse. And it might feel a little bit funny, because in this line of recursion, oops, my inequality is pointing the wrong way. So if my array is of size 3, I have to do find minimum of my array and then the part that changes now is you're chopping one off. In this case, I can chop off 1 off the end. I do size minus 1. Okay, this thing's going to return a number though. If this minimum of, like, say my array of size 2 is less than ARR of my last thing, size minus 1, okay, return something something. So this is saying that minimum number from finMin is smaller. Then within here, you have the other case. You do some other kind of return. Yeah, that's my hint for this recursive find minimum function. This part looks a little funny. We think that, or like the recursive bit in this part is inside an if statement. It's not so much the return down here. Okay, hope this helps. I didn't want to reveal everything. Start with the base case and build up to get what this is doing. Like try working through this part with an array of size 3, and then try it with an array of size 4. Okay. Any other requests? No? All right. So in this class, I will talk about this binary search. We will step through the process again and again. So it may feel a little bit repetitive. I'm trying to find like here, right? So in the classroom, if we were in physical school, Mr. Simon has this nice activity with cups that are numbered, and inside a certain cup is a piece of candy, and you would physically point and walk through this guessing game, which is really binary search. And if you get the candy, or if you get the number, if you get the process right, then you get the candy. We unfortunately can't do that, so instead there is like a numeric example, some slides with colored boxes. It's exactly like the widget, except now we're paying attention to like our left and right indexes, because that's part of how we code it up. So notice here, if you were following through with binary search, we're looking for a number 31 inside this sorted list of numbers. We don't know what's there. All we know is it's sorted. If you're following through with binary search, we have to cut it in half. Where is the middle here? Notice down here, these are indices, middle of 10 numbers. So there's kind of some choices, right? Like it could be either one of these things being our middle because it's even. In this case, where do we want to guess? Let's guess 4. Okay. So between 0 and 9, our guess is going to be in position 4. We see that it's 39. And right now, since we're searching for 31, 39 is too big. And because this thing is sorted, is my number in the left or is my number in the right? Where's 31 going to be? Yep, the number is going to be over here. Yeah, it's going to be on the left. So then notice how your indices change. When your search happens, your high index is no longer 9. We've eliminated all that. Your like the upper bound of where your number could be is now in position 3. So see how that elimination occurs? At first it goes from 0 to 9. Check the middle, that's 4. And then down here, once you checked 4, your high becomes position 3. So then of these two numbers, we got to be consistent. Where's the middle? Which one should we guess next, 1 or 2? Last time we guessed 4 as the middle of 0 and 9. Is it 1 or 2? Where's my next guess? Position 1 or position 2? If we're guessing 2, now that would make your code inconsistent if we guessed position 2, right? You should be guessing position 1, as you notice that 0 to 9 we guessed 4, not 5. The code would have worked if you went with 5, and then in this step we would have to guess position 2, but to be consistent, middle is like the left, right? Out of these two numbers, we choose the smaller one. So now from 0 to 3, our middle is 1, position 1. We see the number 14, so then again, am I eliminating the left side or the right side? Which one gets ignored if I guessed 14 in the sorted list? Good. Our elimination occurs on the left side. So now our low index changes. But notice we've already seen position 1. Okay. So our low position got updated to be position 2. Now where is our guess? Should I be picking position 2 or 3? Where's the middle? What should that guess number be? Only two choices, 50-50. Okay, so you thought about it. You have your guess of 2 or 3 in your head. So we should be guessing position 2. Remember, middle in this example is the left one, the smaller of the two if ever we have a tie. Yeah. So then we see 22. And now the algorithm still keeps going. Right? At this point, our high equals our low number. We have one number. High equals low. Where do you think, if 31 is or is not in my array, we only got one more choice left, right? When there's one number, we have to guess position 3, and we ask ourselves, did we find it? This number, it happens to be 31, but it could have likely been like 28, in which case we would not have found 31. We have an answer to our question. It's there or it's not there. So we could step through this example again, but we're getting close to time. These slides are especially useful because it shows you the high, low, and your guess. When you are writing the code for BinarySerach, we give you a lot of it in the later slide. This is one of the confusing parts of it. How do you update your high and your low and your guess? For the guess, you must be consistent. Like in this example, we chose the smaller out of the two when we have a tie, when your array is even. Life is easy when your array is odd and you distinctly have just one middle. And so, yeah, 4 minutes, we can step through this next example. Okay, so let's do that once more. You're paying attention to the high-low indices, right? I think the array is the same. You look at position 4, that's the middle of 0 and 9. Okay, you see 39, so you eliminate all those numbers. My answer must be in positions 5 through 9. Notice that my low got updated. Instead of 0, it's now bumped up to 5. Okay, that's where I'm going to search. I need to find the middle of 5 and 9. Yes, this one, notice that it's odd. It's like there's only one choice here, right? 7. We check position 7. Okay, we're looking for 73. What happens to low? Where's your new low number? You eliminated the left, right? But you've already checked position 7, though. You know that like 7 is not what you're looking for. So that's why your low index is where you're going to go. 8 to 9, yeah. And now we go through the dance. 8 and 9, you gotta pick one. So would you pick 8 or 9? Be consistent with what happened before. Darn it, okay. So the student that's answering is consistent with the numbers you pick. You always pick the higher out of the two. In the slides, it picks the lower out of the two always. So in this case, we guess position 8. We see 72. Our low updates itself. The high and the low are equal. Okay, we only got one choice. So is the number, at this point, do you know that 73 is in my array? Nope. It could be some other number, right? It could be 88, 100. So we still have to do one more check. You're not done just yet if your high and low indices are the same. You still gotta go and guess. You have to peek and see, oh, darn it. We look at position 9 and we see 89. And at this point, notice that your high and low positions, now they're like the algorithm still steps through these. Your high is less than your low. What does that mean? Have you found your number? Yeah. So your indices have crossed each other. Yep, it can't be found. based on your high and low kind of guesses, 73 can't be a part of your array. It would have been between positions 8 and 9. Okay, so these slides with these orange and purple boxes will be very helpful for you when filling out this thing for binary search and binary search list and coding bat this week. Fill out the question marks, and we've given you a lot of what you need for binary search. It's like fill in the blank. That concludes today's lecture, Block 1. Take care. Stay warm. Have a good one. See you on Friday. Bye-bye.